This is Computing Up, conversations about computation writ large, with Michael Littman and Dave Ackley. This episode was recorded May 22nd, 2023.
Hello, anybody there?
I'm here.
Yay! So
Michael.
I've been told that it's been a while since we've had an episode. Is that actually true?
I believe we've missed 2 months in a row.
2 months?
Yeah.
Man, that's a long time.
Although the last one was Mike Levin, which was super fun.
Right. Well, probably it was just hard to follow up on that.
Yeah, that's right. So we didn't try.
So we didn't even try. Yeah. Well, we're trying now.
Yep, we're back.
Well, welcome back.
Well, thank you, and you too.
Thanks a lot. I wonder if maybe we should talk a little bit about why we've like I didn't even notice, to be honest, that the time had passed this fast. Every week it's like I'm just trying to get to the end of the week, and then
I perceive that you have had a step up in average busyness. How
about you?
Well, it doesn't feel like a step up. It feels like just more the same.
I see. Step across.
Something like that. Yeah, I mean, little bits and stuff like that. And the older we get, certainly, the faster the weeks go. The weeks turn into months going, and so on.
Boom.
Here we are.
My grandfather-in-law used to say he would snap his fingers. He would say, "As you get older, time goes like this." And we were like, Grandpa C, shut up. Like, that's just so weird. Stop saying that. And he was totally right.
Did he actually make any noise with his finger snapping or no?
Oh, you probably couldn't hear me.
No, I couldn't.
This is a Zoom trick. Yeah, so I keep forgetting that this is true. Like sometimes I have people on and I applaud for them, and Zoom completely filters it out. So it's like I'm just staring at them in silence.
So you're not hearing snaps?
Oh, I'm hearing snaps. How about applause? Yeah, try applause. Try clapping. Yeah, so yours isn't filtering, but mine.
No, nothing.
Isn't that weird?
That sucks.
I mean, I think it's great, but it's also terrible.
Whatever. Like that.
This is the joy of AI.
Well, it's certainly using AI to do a dubious sort of thing to help you whether you want it or not, that kind of thing.
I feel like that's the problem.
About go ahead, sorry. How, if both people are using headphones, then why does Zoom have to mute the other person? The Zoom decides who's talking, and it mutes everybody else, whether there's any reason for it or not, and that aggravates.
So, but does it not know if we have headphones on? I guess
I would think it ought to be able to figure that out. Because the echo canceling, the feedback loop where it's trying to figure out what the delay is that it needs to cancel out, and the answer is nothing. There's nothing I don't have to cancel out like that. Anyway.
Or at least nothing this second. Maybe in a second from now, it'll start to be an issue again.
That's true. But then it could be watching like a hawk to see if feedback, echoing starts to come in, then it can react like that. It just doesn't want to, because it's all thinking about big groups and everybody being robots and taking turns and all this stuff that's not true of real conversation.
I mean, yeah, I think that's a good description.
Anyway. So put it this way. What have you been busy with? What have you been up to?
Well, I feel like it's a lot of conversations kind of like that one, where I start to think, okay, but people come to me and they say AI is terrible and it's doing terrible things. And I feel
is that your modal conversation these days?
That is my modal conversation. That is the peak of the distribution. I have one of the folks that I work with at NSF has taken to calling this period of time since like the middle of April, thereabouts, maybe a little bit before that, as AI everywhere all at once.
I still haven't seen that movie, but
it's a really good movie, right? Exactly, it's a good reference to a thing that's fairly current. Like it won all sorts of Academy Awards and stuff,
right?
And so I asked her, like, oh, can I use that line and credit you? She said, you can use that line, but don't credit me. I don't want to get in trouble. So this is kind of this is another modal conversation I have at NSF. Which is that there's a tremendous amount of conservatism in the sense of like not wanting to go too far out on a limb.
As far as having an opinion on AI?
Well, no, in this case, no. It's what she expressed to me is not that she was concerned about the opinion on AI. It's that, well, it's kind of making reference to a movie, and like, what if the movie people come after
Oh,
NSF?
oh, I see. I see.
Like, you're taking our name in vain.
I see. You're degrading our copyright, our trademark, or something.
Right, right. And I feel
Like
like
that.
that's not how jokes work. But maybe, but I mean, that is how the federal government works. Like, you want to be
And that
super
is how
careful.
lawsuits work. So
Yeah, I
yeah.
guess.
Well, yeah, I mean, certainly one of the things that I perceive is, as people rise in management, which, that's what you're doing, they have to become more political. It's just the nature of the thing. They have to be more careful about what they say. And if they just keep shooting from the hip, like being genuine, sooner or later they screw up or turn into Republicans.
You
Anyway.
get bit on the butt.
Uh-huh. AI everywhere all at once, but I can say it because I'm nobody. Like that.
I
Yeah,
don't
I
know. You
mean,
have a podcast.
it's unbelievable. Yeah, well, we have a podcast that is very, very secret. We've done a
That's
very
right.
good job hiding
Oh,
our podcast at the
we
bottom of a deep well.
we share it with only the coolest people.
Only the coolest of people. That's right. And they know it. We know it. And if everybody starts finding out about it, it's gonna just suck.
It's true. And
And
we'll have to talk conservatively and be
But
conservatives.
so for me, it's like my sister, and I get along okay with my sister. She's in another state, but we don't have a lot of contact except like birthdays and whatnot. But now she's sending me all this AI email, thinking that I've got to be interested in this about the latest thing that Bard is doing, or this great opportunity to use Bard, or whatever it is, and I'm like, yeah, okay, I get it, like that. But that's a new high watermark for sure.
Yeah,
So
yeah, I agree.
everywhere it has reached my sister.
Right, it's reached Dave's sister. That's really interesting, and I feel like it's everybody in the field is feeling that. And so I actually, the place where I wanted to use that line, and I did actually use the line, but I didn't credit the person who invented the line, is that I started writing a monthly kind of update note to whoever signed up for my divisions, the IIS division at NSF's emails.
IIS is
Information and Intelligence Systems.
I see. Okay. Right. So you write a little from the director thing or whatever.
I call it STEM update because I send it out on the second Tuesday every month.
I see. Very funny.
Thanks
Not
very much.
Science, technology, engineering, or mathematics. None of that.
None of that stuff. Right. And I talk about kind of like, I feel like a visitor to Mars sometimes. Like, there's a culture here. I'm not really, well, I'm becoming part of the culture, but there's still enough of the old me around to be able to say, that's weird. I don't know how to think about that. And so I write stuff in this message that is just, things that I've noticed, things that are on my mind, things that people have asked me about. And I've been getting a lot of, about 1 in 1,000 people responds. And I say that because there's 12,000 people on the mailing list, and 12 people roughly respond each time. But 12 people responding is still like, there's interesting people with interesting things to say. And the kind of major response that I've been getting is, wow, you make it sound like NSF is populated by humans.
Which can't be. So that's interesting.
That's surprising to me. Yeah. How do you make it? Because most of the communications that come out of the NSF are written in that style, where it's like, this, I don't want this to be possibly misinterpreted. And if it is misinterpreted, I want to not have any liability associated with that.
No fingerprints.
And I'm talking like I talk. And that's, so far it feels like a high wire act, because I feel I could definitely step over a line and I am toast.
Well, but one of the salient features of Michael for me is that you're actually a nice guy. And so you'd be less likely than many, I think, to accidentally step over the line by being a douchebag like that. So you have a chance of being a little more human and still staying on the right side of the line.
Okay, well, I hope that's true. I hope that I'm able to continue to do that, because it's been really fun, and I deal with issues that I don't know, I think are interesting. Like I tried to explain the structure of NSF as an organization. It's an awful lot like a university, but all the names of everything are different. There's
Sure.
there's a president, there's a provost, there's a board of directors, there or whatever. Like what do they call those people? It's not board of directors.
Deans,
No. Like the like external people who are kind of oversight. There's like a
advisors,
like
advisory
that
board.
advisory
Uh,
committee. And then and then there's deans, and then there's department chairs, and then there's faculty.
uh-huh,
And like I'm a department chair. So you
uh-huh.
talk about me kind of going up in management. I'm actually kind of flat in management. I was a department chair already, and I'm roughly a department chair again.
Uh-huh. But then NSF's budget is a little bigger than most universities.
It
So,
is. I just talked to a former division director, like someone who had roughly my position, and is now back at the university, and he's doing research budget stuff.
uh-huh.
And I'm like, how are you finding it? Kind of upon reentry to the regular world. And he's like, it's fine. I'm using my skills. It's been surprisingly easy, except when I look at the budgets, they have one too few zero in them.
Yeah, they all lost to zero.
They all
Yeah.
lost to zero. It's like, oh wow, yeah, we really are dealing with big quantities.
Yeah. For good and for ill. I mean, that's the potential is you can do bigger things, and the risk is you can waste bigger chunks.
Well, I have computed that I have declined $647 million in funding so far.
Wow, that's a lot of savings.
That's a right. Think of what I'm doing for the American people. Or
Uh-huh.
on the other side, think of how I'm screwing over the research community with all those rejections.
I
Uh,
mean, is there a sense in that applications or proposals or whatever are like just exponentiating every season, and now there must be Chat GPT proposals coming in. That people just wrote up, asked Chat GPT to write them for them, and then they send them in.
So this is a concern that has been expressed. You're not the first person to have said that to me, and it's definitely something we're watching out for. We have not seen any evidence that we don't see an uptick in proposals, and there's been no indication that the proposals are kind of have that sort of weird 5-paragraph style that ChatGPT
Right.
likes to write in. There was an accusation that one of the reviewers, like someone who from the outside came to NSF,
To do a panel
had ChatGPT write his or her review.
of a proposal.
Yeah, so like entered in information about the proposal, sent it to OpenAI, which is what you have to do because it's in the cloud, and then
Right.
got back the text and then used that as part of the review. And so I'm
That
now on
would be
the
bad.
I'm now on a committee to try to work through what NSF's policy is on all things ChatGPT,
Uh-huh.
and so
I would
hopefully
think
we'll
the
have some
policy would be,
guidelines.
that's bad.
Yes, it is. That was
Don't do that.
yes. Don't do that. And the main reason so far is because you have to send it to an
Confidentiality.
external. Yes, exactly. That we
Yeah.
promise that when people send proposals to NSF, we keep them locked down and we have them destroyed when they're no longer needed. And that would violate that, so people shouldn't do it.
Right.
To be clear, this did not happen in my
Your division.
directorate. Definitely not my division.
Directorate.
So it wouldn't impact anybody who's probably listening to this. But we're on it. It's it's a concern. But writing it, that could create a huge problem, because if people are just knocking off proposals left and right, that's one concern. Another concern is that somebody wants to make a business out of that and then does like a FOIA, like a Freedom of Information Act request to NSF saying, hey, send us all the proposals so we have training data.
Very
And that would
tricky.
be a huge mess. And that has not happened. And I hope nobody listening
No
to
one
this
gets the idea from
yeah.
listening to it right now.
Right. I think it's a
but,
terrible idea, but it also would make a big mess.
I mean, how could NSF promise any kind of confidentiality if all it would take is a Freedom of Information request to break that confidentiality?
Yeah. So my understanding is that the policy so far has been FOIA requests do not apply to rejected proposals or not yet accepted proposals.
I see.
So most of what you send in is fine. There's still reason to complain about allowing accepted proposals to make it out the door. And so I'm hoping to talk to some of the powers that be to try to understand that decision and see if it could be changed.
I mean, certainly if it gets funded, then it's public money, and then it's a different sort of thing.
Yeah, but the proposal document is not that thing. So what is made public is the abstract.
The contract, the grant itself.
Yes, that's right. There's information about the grant, but not the details of the proposal. That's still supposed to be private, I think.
I see.
But you're right. It becomes a fuzzy line. Once it becomes public money, it's a public project. It's just a question of, would somebody still want to get a hold of it en masse?
Right, exactly. Well, and there's a lot less of that than there is of the proposals that were rejected. And you could do both sides training. I'm not sure what it's called, where you have positive and negative examples, right? Like this one and not like that one. Discriminative training,
right? So you have two classes that you can separate, and that does seem like it would be really helpful for being more accurate.
Well, so one of the places that I sent my science fiction story to that rejected it in 47 hours or something like that.
Oh wow!
I think it was actually more like a whole weekend, but whatever. And because they have a slush pile that they really work on to get through it, they have been buried with science fiction stories written by ChatGPT. So much so that they've actually, for a while, they shut down their slush pile submission queue. Now they've reopened it because they think they've got little detectors that they can find most of them, which they're refusing to tell us how the detectors work, because then people would get around them and so on and so forth. And it's the whole ridiculous
security by obscurity.
Exactly.
That's really interesting. Yeah, it's an interesting case, right? Because it doesn't cost you anything other than the effort to create the document to submit something for review. Right. And so that really puts the incentives into place where, if I can generate stuff faster, then there's I get more bites at the apple.
Exactly.
So people, I've heard this argument in the context of like spam on the internet too, right? If it's not costing you anything to send an email, you can send as many emails as you want. And one of the fixes that people have proposed is basically charging, like not a lot, but just enough that it makes it so that mass sending is not as, it equalizes the two sides of the equation better.
There's this checklist that's gone around about email, about how to fix spam. And the checklist is sort of like a Mad Lib kind of thing, and it says, your proposal to fix spam will not work. It is based on charging, using proof of work, and it's got all these things which will not work because you would just create a whole new infrastructure for and so forth. And I think that's kind of the problem, is that how do you actually charge people, and that means everybody has to be on the record, and you have now it's might as well be fucking cryptocurrency or something like that.
I like that it's sufficiently trodden that you can actually make a checklist like that. That's awesome. Okay, well, I take it back. I no longer believe in my proposal.
It's all just how implementation details. And that's never any fun.
Wait, so why does society work at all? Like there's so many ways that everything could be broken and that are. So like, because most people aren't douchebags most of the time?
And I think there's evolutionary support for that, because the whole idea of build bottom up, the whole idea of robust systems is that you make systems out of other systems. You don't start with parts that are inert and make a machine and call it done. You start with little systems and you make it bigger systems. And each of those little systems has their own goals and agency and homeostases and ability to heal and ability to recover and all that kind of stuff. And that just gives a toughness to systems that are built out of these things that stuff that's built out of parts can't approach like that. But it also means there's this incredible overhead because it's like, a million little cells are deciding, do I want to do the next step in my thing that I'm supposed to do? Whereas, random access memory, it doesn't have any problem like that. It has a 1 recorded there. It's a 1 and it's sure like that. So,
this
Robust
reminds
first.
me. Yeah, I was going to say the
Go ahead.
robust first and efficiency. Like efficiency is sometimes the enemy. This is a philosophical stance that I've started to
Sure.
absorb from you. And so we often in my division we're talking about, well, how can we be having greater efficiency,
Yeah.
efficiency, and I've been starting to push back and say
Yeah.
sometimes we don't want efficiency. Well, so and one concrete example of this, which hasn't actually changed anything because the world is what it is, but it's changed
Yeah.
my perspective on it, which is that some people worry. It's like, what if we've already funded something like this before? What if there's some other university that's already gotten money to do this specific thing? Like, isn't that wasteful? Isn't that somehow inappropriate? And I'm
Right.
starting to feel like no, like it's kind of okay for different groups to or even different subfields, right? To address similar problems in their own special way. It kind of is creating all these I don't know, crossbar connections that make the whole thing more real. It's less brittle,
It
less
sounds right
single
to
point
me.
of
Yeah.
failure. And so it sounds wasteful, and we don't want to be wasteful, especially with the taxpayers' money and everything. But there's a sense in which I don't think we need to be like so vigilant about this issue of redundancy, like
Right.
squeezing out all possible redundancy. I think that there's positive reasons to actually allow there to be some of that in the system.
Well, so it's the computing creed, and the third statement of the computing creed is just as important as the first two, but it comes third, and it's as efficient as necessary.
Mm,
Because sometimes you're going to die. If you run out of gas in the desert, you're going to die. So you need a car that gets 40 miles the gallon or whatever the hell it is. So if you need to be efficient in order to accomplish something, then you be efficient.
right.
But a lot of times you don't. A lot of times, so first be robust, then as correct as possible, and as efficient as necessary.
There you go.
That's the computing creed. And people do the correct and efficient creed instead. First be correct, then as efficient as possible, and then as robust as necessary.
Ah,
And I think that's for a lot of systems, that's a mistake. For first be correct and as efficient as possible is fine for small systems. That it's okay for them to break because you're going to throw it out and get a whole nother one. But for systems that actually need to survive, like society, then you want to be robust first, correct as possible.
right. Does the failure create mass destruction, or is the failure kind of like like
Just
a little like a boo boo?
right,
And if it's mass
exactly.
destruction, you probably want to be a little bit more robust. So I think this is this is not making it into the public conversation quite so much, but I wish it would. Which is, I think a lot of the concerns at high levels are about what kind of damage can AI do,
Right.
and the way that that's often framed is, sort of that AI is evil or AI is dangerous and we need to protect people from it, and not, okay, well, what can we be doing to make this, when we apply this in the world, when we actually put it into practice, that it is as robust as possible, that we've checked everything we can check, we've tried to manage the unforeseen consequences and try to foresee them as best as possible.
Yeah.
Like getting that kind of mindset. But I feel like it's at the level of putting it out into the world where that's most important.
Yeah.
And the AI is getting painted with that brush across the board. And I've been trying to separate out. There's like sort of fundamental ideas that we can explore and not really worry about so much. And then there's actually putting it out of the world and touching people's lives, where it absolutely has to be as safe as it can be.
Well, I mean, or the trade-offs have to be understood, they have to be explored, and so forth. Yeah, I mean, I totally agree. The problem is it's it's not AI, it's everything. It's every technology, it's every piece of science, every that we focus on the tool itself, and we say, is this a good tool or is this a bad tool? When of course it's fucking neutral. It depends on what you do with it. You can use it in a good way. You can use it in a bad way. But that part, the people who are doing things don't want to talk about. People want to reserve the right to decide how to apply AI. That's their secret sauce. That's their startup magic. That's going to make them $1 billion, like that. And but that is where the good or evil is going to come from in the implementation details of what are they actually going to bring to market? What are they actually going to put out 1 million copies of? You know, one little AI sitting in a little computer someplace talking to nobody is not a threat, no matter how smart it is. It's not until it gets gain. It's not until it gets amplified that it matters. But nobody wants to talk about that part because that's kind of the whole capitalist thing. It is, you know, you come out, la, 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 and nobody ever thought about, you know, why I was buying all this land and digging all these holes in the ground. And it turns out I was making canals so that I could move barges extremely cheaply compared to everybody else and undercut everybody else's freight transportation costs. Boom. People try and do the same thing with AI.
Yeah. Can I ask? Can I tell a quick canal story?
Sure. Let's talk about canals.
So I think one of the I want to say one of the weeks we missed, but I guess you're saying we missed months, so this is not a valid excuse. But anyway, I did
now.
Yeah, and time. I'm snapping. You can't hear me, but I'm snapping.
Right.
Went to Scotland for about a week, and that was pretty cool. And we saw a bunch of lochs, you know, like lakes. But two of the lochs were connected by a canal that had locks in it, which was protected by a lock. So that made me very excited. I took a picture of that. That was my favorite picture of Scotland.
A lock on a lock between locks.
Right. It's a lock. And right. So, but the point is that these canals were built for, I think, a very similar scenario to what you were describing. Somebody decided this is going to be really important for commerce, and they wanted to build it really carefully and do the right thing. And they had the lock system all set up, and they constructed it, and it took a bunch of years. And by the time they were done, railroads existed.
Is that true?
No one ever used the canals for commerce. Like by the time they actually got it up and running, it was not useful.
It was trumped by trains.
By a better way to do it. Yeah.
I mean, the story I had gotten was that, I mean, maybe those particular canals that you were looking at missed the boat, so to speak. But I feel like some people made out like bandits when in the early days of canals, that there were decades or whatever, I'm not sure, where before trains were on the scene, before train tracks were on the scene, where you know, they undercut everybody else in terms of price per ton per mile or whatever the transportation thing is, because they could move 100 tons with a donkey or whatever it is. But sure, and it is a funny thing, though. I mean, canals at one point are so unbelievably efficient. They're so low friction compared to a train, which is just so dumb. But the trains are faster.
Right, and coal is plentiful and has no repercussions to the environment.
No downside.
Yeah, no downside at all.
It's just given to us by God to go nuts like that. I mean, that I was actually thinking about that, not to take us even yet further afield.
Down the canal.
That, you know, evolution, you know, doesn't plan. Evolution just does its random thing. And, you know, there were all these plants that came out of the ocean and were trying to colonize the land. And it was hard to fight gravity. It was a lot easier when you were in the water. But eventually somebody invented cellulose so that you could actually stand up against gravity. And cellulose and related chemicals, I guess, were so chemically strong that they didn't break down. There was nothing that could eat cellulose. And that's where coal came from. All this unbelievable amount of carbon getting made into cellulose and then not decaying, and so getting locked up in the ground until eventually, whatever it was, bacteria, fungi, whoever the hell it is, somebody figured out a way to eat cellulose, and then they were really happy. But all of this carbon was buried in the ground until we came along and said, you know, let's take that cellulose and put it back up in the air. And, you know, ain't it just the way things work? Like that, you know, you thought you had it stocked away, and then, you know, these little munchkins show
up. Change the game out from under you.
Change the game, yeah.
Well, speaking of life.
Indeed.
I was wondering if you could kind of maybe fill us in on what you've been doing. And in particular, I think you were building up to writing a paper for the Artificial Life Conference.
Yeah, that's true. And so to start at the end and work backwards, the paper was, I wrote the paper, it was accepted
Oh,
for an oral presentation.
oh
Uh,
yes, oh
um,
yes.
and I turned in the camera ready copy, the revised camera ready copy for it yesterday.
Oh,
Like
congratulations.
that. So that's a little bit of a load off.
You know what that brought to mind immediately is sitting in your office in Morristown with
At Belcour.
at Belcour with rubber cement, getting ready to do camera
Cut
ready
and
copies.
paste.
Where we literally we had scissors, we had, or I guess a razor, and we had the rubber cement that you were so
Get
adept at
high on.
manipulating. Yeah, right.
Uh-uh.
That you would that we and that was like the office
Wow.
smelled a certain way when it was camera ready day.
Wow, I'd forgotten that somehow I had imagined that laser printers always existed even
Always
back then.
existed. Well, there
Uh,
were. I mean,
well,
we
there
did
was
laser
something
print. Oh
we
yeah,
were something was coming up with the text boxes that we were cutting and pasting,
yeah.
like that.
Totally, totally.
Why couldn't
But
we just print
they
another
wanted
copy?
paper. We had to actually mail them. We knew where all the FedEx drop-offs were, because
Wow.
if you're this close to the deadline, you can go into Morristown proper. If you're this close to the deadline, you could just do it in the building. But if you're this close to the deadline, you're gonna have to
You
drive to
have
the
to go
Newark
to.
airport.
Uh, that something says I'm a little bit familiar.
Anyway,
Anyway,
so congratulations for doing that and not having to go to the Newark airport.
well, we shall see. And so the conference is in Japan, and I'm not going to travel, so it's going
Hmm.
to be an online presentation for me. I just registered for the digital experience rather than the in-person conference, and
Gotcha.
but yeah, it was really kind of fun. So that the title of the paper for references, a robust programmable replicator
Ooh.
or an indefinitely scalable machine.
All right,
Like
that last phrase I recognize because that's a phrase that you use to describe
indefinite
your
scalability is the
tiles.
the model, yes, the movable
Yeah.
feast machine, the T2 tiles. That's all about being indefinitely scalable.
All right, and
But
what's
a
the first part had to do?
robust
Okay,
programmable replicator.
because
Uh,
replicator is easy. You can replicate all day long. So programmable replicator. Okay, I don't know what that is. And then robust, like what makes it robust versus not robust? Okay, all right. So
yeah,
I'm intrigued.
yeah. So programmable means it has some genetic code,
Mm.
something that you could keep the physics the same in principle and just change this ordering of this information on this part of the thing, and it'll do something completely different, like that.
But it'll still
And
replicate somehow.
well, in fact, it's the program that you write in this thing is what's guiding the replication. It's
I
what's
see.
causing it to happen. It can't replicate without it. And if you were to make arbitrary changes to this
It would not replicate.
information, it may or may not replicate. But based on experimental data or based on anecdotal data that I now have, because the movable feast machine simulator has an X-ray command, Control X, that just flips a bunch of random bits anywhere
Hmm.
in the simulated space, and you can see what happens. And so when I have a population of these replicators that have grown and replicated, and they're all jostling with each other and saying, "Wow, I wish this thing was a little bigger so I could have a kid," like that, and I hit it with some X-rays, the cell bodies, which are in the shape of diamonds, uh, um, they almost invariably survive, but the code inside very typically gets destroyed,
Oh,
and because it's fragile, the code is fragile, and whereas the cell body and the cell membrane, I mean, they're not really cells, and I have air quotes around them cells because I don't want to piss off any actual biologists,
I think
so I
that's.
call them I
I
call them
think
diamonds.
I think
uh,
Zoom actually kind of got rid of the air quotes when you used them, so that's why people couldn't
uh,
hear them.
they were edited out
Yeah.
with the video, and so diamond. So
Okay.
the figure one shows that it's a diamond replicator. And the reason it's a diamond is because the shape of the thing is determined by how many distance from the center, using Manhattan distance.
Got it.
And Manhattan distance makes diamonds.
So it's a circle, but in Manhattan distance
It's a
space.
circle in Manhattan distance. That's right. A circle
Okay.
in Manhattan is a diamond. Makes perfect
Gotcha.
sense. And I like the fact. Well, anyway, that's a side issue. So there's just a tremendous ton of code to allow you to build these diamonds that are quite big. In the movable feast machine, when you have an individual little event, like one tiny little update, that can affect at most 41 cells, 41 sites. I can't say cells there, like that, which is a Manhattan distance of 4. 4 sites in any direction adds up to 41, including the center square. Like that. And that's it. And if you want to do something that's bigger than 4 sites away, bigger than 41 cells, you have to do it over multiple events. You have to figure out a way to break it down into small enough pieces that they can communicate information with each other so that they know where they are. And these diamonds.
That sounds like a really big step, because now you're going from this sort of hard programmed local connections to being able to kind of layer up and build structure on top of that structure, and then
be able to scale up. Well, who knows?
Yeah.
Be able to scale up to bigger things somehow. And yes, absolutely. And I've learned a ton about just the obvious techniques that you end up using over and over again, like creating a gradient. So you say count a number, just count 0, and then everybody next to you, they look at everybody they've got, they find the minimum number, and they assign one bigger than the minimum number. And everybody just looks at all their neighbors and then assigns themselves one bigger than the minimum thing they see. And that's in fact how the cell grows. Is that the root in the very center has a hop count of 0, and everybody around it has a hop count of 1 and 2 and so forth, up to whatever the size of the diamond is, and it makes a diamond that's so big. Huh. And in these diamond replicators, by the time they reach the size that they're going to split and turn into 2 diamonds, they're taking up over 5,000 sites. So
wow.
you've got 41 sites for an individual tiny little transition that you can just directly code, up to over 5,000 sites, which is how much is being coordinated by one of these diamonds. And then you have a whole population of the diamonds that are all growing different sizes, and they're all competing with each other for space and all of that. And it all works. And it's
on the first try.
Yeah, that's right. The first 20 years was enough to make it work, and I don't have to try another 20 years like that. Yeah, it's not easy.
Yeah. That's what I was imagining. I didn't mean to be flip about that, but it just seems figuring out how to, because I don't know. I remember taking a little bit of biology and remember hearing about these different mechanisms by which cells like coordinate and communicate with each other. And it didn't make any sense. And it didn't even seem like it could possibly work. And so somehow making that actually computable, right? Where a computer could execute these commands and it would actually sync up. That seems like quite a proposition.
Well, it feels, just between you and me, it feels pretty fucking awesome.
Good.
It really
that's
does.
Nice.
And I don't know how many people are going to get it. And one of the 3 reviewers didn't get it. So I got a weak reject, an accept, and a strong accept.
Oh, nice.
Those were my 3 reviews for the conference. And the weak reject was looking for a traditional top-down. You must give a research statement. Figure 1 should be nice and clean, like keep your desk clear and all that stuff. And kind of dismissed the paper as, they backhanded diss to say that if you did what I suggest, what the reviewer suggests I should do,
then you'd have a good paper.
It would rise above a tech report. was the
Oh,
phrase they used. Like that.
oh,
And it's like, oh, yeah,
that's an academic burn right
yeah,
there.
that's low. Uh, um, but
Wow.
in a way, I asked for it because I did put a few zingers in the text against the top-down people, against the theory people, the formal people, and stuff like that. Uh, um, so I was kind of asking for it, like that,
So you think
and
you got a theory slash top down reviewer?
it was seems pretty clear
Okay.
from the nature of the comments and
I
stuff
see.
like
I
that.
see. I see.
And anyway, but it was accepted and so forth, and it's all fine. And I toned it down maybe a little, and put some backhanded pseudo apologies in to diss back. But on the one hand, it's just a demo. It's not like I think these diamond replicators are the way that all future movable feast machine computations will be built at all scales. Although they might,
Yeah.
or some subsequent thing. But everybody wants to know where's the evolution? Does it evolve?
Uh,
Like that, because that's really important in the frame of mind of artificial life folks.
right.
An
Right. Right. Right.
awful
Right.
lot of them are studying evolution, and they say, yeah, what about evolution?
Right. Come
And
back to
and
me when. Yeah.
and my reply is no sign of it so far. Whew. Uh,
Oh,
uh,
nice.
uh,
Right, because there's nothing stopping an evolutionary process from happening here, right? That you could imagine the bits are getting flipped, and so it could
well,
very well be the case that a different program gets written at some point.
absolutely, and the underlying execution engine, the movable feast, is only provides a best effort guarantee. It doesn't actually provide to be deterministic. So even if you don't hit Control X and create deliberate bit flips, just because of racing between the things, it could be possible that an event could get screwed up and so forth, and it could make a change that would be seen on one side, seen on one tile, but not seen on the neighboring tile. So they would have inconsistent views, and then they could step on each other from there. And again, the MFM engine tries hard to avoid that, makes its best effort to avoid that, but it can't guarantee it because it's
Right.
actually racing. The tiles are physically racing with each other. There's no overall synchronization and so on.
And it's pretty much guaranteed that if you run it for a billion years, something's going to happen.
That's right. Like that. So,
Wait, can I a quick clarification question?
sure.
So you have, as I understand it, you have actual physical hardware that implements this sort of tile architecture, and you
Yes.
have simulators.
Yes.
Does this diamond replicator run on just on the simulators?
No, it runs, well, both.
Okay.
And, I developed it on the simulator because it's at small scales. So the key is a tile. The key is a hardware tile that is going to represent a certain amount of computational resources, a certain amount of sites for automata to work in, a certain amount of computational real estate. Yeah. And the key point of a tile is that it has to be able to plug together with more of its own kind. Like that. And in particular, if it's going to be indefinitely scalable, it has to be able to plug together with an indefinite number of of its own kind. So there can't be unique serial numbers on them. There can't be a privileged head node, or anything. They're just grains of sand that you lay them out. In fact, you can even add more while the program is running, and it has to deal with that somehow. And I've got some demos where that actually happens. And sometimes it works, sometimes it doesn't. The engine needs work. And so we have these
That's
tiles,
awesome.
but we start out the simulator. If you're only simulating 2 or 3 tiles, the simulator is a lot faster than running on the actual tiles. But now the T2 matrix, that the real hardware thing is at 76 tiles.
Oh, nice.
Which is, it's not huge, but it's a significant chunk. And it might still be the case that if I tried to simulate 76 tiles in the simulator, which I could more or less, it might still be a little faster. But not a ton faster, and there will be a crossover point at some place.
Right.
We still have more T2 tiles that we could build into the matrix, but I'm sort of going step by step. I'm also a little afraid of blowing out the house wiring,
Right, because you don't have
we'll
indefinite scalable electricity.
Do not have indefinitely scalable, because the indefinite scalability is based on 4 givens: power, cooling, real estate, and tiles. And if any of those things run out, then your machine doesn't have to be indefinitely scalable anymore. But as long as you have power, cooling, real estate, and tiles, then nothing else can stop it. You can't run out of addresses. You can't run out of distance from the center or anything.
Yeah.
And so the paper that I submitted is about a case study, a 20-day case study of running this diamond replicator on the T2 matrix. And you know, it was all completely concrete. The first replication happened after 19 and a half minutes. So I plopped down a single atom in the grid. It was all empty. I plopped down a single atom that created a loader. Created an empty cell with a special thing in it that gradually grew a loop, that it inserted one instruction after the other to create the initial copy of the program code called the ancestor that I wrote. I wrote the ancestor, and the loader construct built the first diamond and gradually loaded it up a loop inside with the code of the ancestor. Then the loader erased itself, and that was it. And then from then on, it was the program loop running and saying, okay, now we have to move the code over to the left-hand side of the diamond so that we get out of the center, because when we split, the center is going to be cut. And then we have to make a whole nother copy of the code from the left-hand side all the way to the right-hand side, because we're going to have 2 daughters, a left daughter and a right daughter, that each have to have their own copy of the code. And then once we have those 2 copies, the diamond has to become big enough that we could then cut it in the middle and essentially cut it into 4 parts, 4 subdiamonds, and the north and south subdiamonds wither away, and the east and west subdiamonds become the daughters, like that. And then the whole process repeats.
Wow.
And, you know, on the T2 tile matrix, it took less than a day. It took about 19 hours before it filled the grid. And there were diamonds all over the place, and they were just jiggling against each other. And sometimes eventually they would pop, and that would free up some space. And sometimes they would get messed up. I mean, they would overwrite each other. There was all kinds of little bugs and imperfections that is in the code in that case study that none of it kept it from running like that, because it had enough gain, 2 for 1, 2 for 1, 2 for 1, that even if some of them diamonds ended up being zombies because their code wasn't functional, so they were essentially just these, like, you know, oily bags full of detergent left floating around, not actually doing anything. Though they would get crowded out by the ones that were still reproducing like that. And so that was a lot of fun. And so that's what I wrote up, the, you know, completely concrete experiment, the case study, like that. And I've got another one going now. I mean, one thing that's fun about this is that, since the whole idea is that it's not enough just to figure out how to make a replicator once. You actually need to build a computational stack with programming tools, debugging tools, programming language support for these things that you need, so that you can keep climbing up to more and more complicated things, bigger and slower machines, because bigger machines, you know, everything is still built on top of those 41 site events. So if you want to do something that's spanning 5,000 of those things, it's going to take a bunch of events for information to get all the way across it. You can't avoid it. So bigger means slower in the movable feast, and it does in real life as well.
I was going to say,
same reason, like that. So now that I have the diamond replicators, I still have tons of programmability left, and so now I'm working on multicellularity.
Ooh.
Once these things split, maybe they don't just head in opposite directions, but like they try to stick to each other or something. And it's turning out to be really, really, really hard. But that's it. And so there's been this long tradition going back to von Neumann of trying to make digital replicators based on these cellular automata models. And this is in that heritage, but I changed a tremendous number of rules. It's not deterministic, it's not this, it's not that, it's the other thing. But changing the rules was essential, as far as I can tell, to getting as far as I got. So now, I mean, hang on. So here's the phrase from the paper. Can you hear that? The boombox car.
Oh, it sounded like an airplane to me.
Yeah. So the primary contribution of this paper is a demonstration that a best effort computational stack employing asynchronous and strictly local updates can produce structures that survive, move, grow, heal, and self-replicate under programmable control, withstanding radical non-determinism, resource limitations, and even bugs in their own code. Oh, that's it. It's fine. It was painful building it. I mean, because the tools, it takes over 8 minutes now to compile the code for this thing. So wow. Change one letter, another 8 minutes, like that. And that's mostly because the code compiles into tens of thousands of lines of templated C++ code, and most of the time actually goes running the C++ compiler to compile all of the stuff that we generate. Yeah, like that. Anyway, wow. So that's awesome. That.
Yeah, I feel like. Yeah, so, I mean, I don't know if you feel like that's a turning point, or it's at least a milestone, right? It's at least something that you've seen in the distance. I remember in like I don't know if it was the first Artificial Life Conference or the second Artificial Life Conference, there was some kind of paper on artificial chemistry, and you said you can't stop there. Like, you want to use that artificial chemistry to build an artificial biology and build artificial ecology, and like you really want to build on top of that. And I feel like you seem to have done it.
This is definitely a big step. I mean, one of the theories of this whole thing is that it's never going to be a complete solution. It's only going to be a solution at a certain space and time scale. And then when you want to go up to the next space and time scale, there's going to be related issues. There's going to be similar issues, but there's also going to be unique issues because of the nature of your lower scale. The nature, if I build on top of the diamond replicators, say, and now I go multicellular, and now we have multicellular organisms made out of diamond replicators and so on, that will change the specific nature of the issues that come up at the next bigger scale. But there's still going to be all these common elements. There's still going to be gradients. There's still going to be communication. There's still going to be local coordination. That one of the things about, I used to talk about how, synchronization is bad. Centralization is bad. Don't do that. But now I have to admit that that's a little bit too simple. What's bad is saying synchronization and centralization are part of the architecture that you're stuck with. That's what's wrong. So indefinite scalability fights that. Indefinite scalability says, no, there is no central, there is no synchronization. But still, now when you're writing code that's running on this thing, and you want to be like a little diamond, a little organism, the organism has to decide whether to go north or south or east or west. And it can't go in all directions at once, right, or it'll tear itself apart. So it has to synchronize at its own scale, like that. It has to say, Joe's the leader for us. He says go west. We're all going to go west, like that. So
right, because the alternative is chaos.
The alternative is tearing yourself apart. The alternative is not having structure at that scale. If you want to have structure at that scale, then there has to be some coordination mechanism. It doesn't have to be a single point, but it's got to be something. Uh, um, and that's what the diamonds do.
Mm.
All the edges of the diamonds have like radar on them where they're probing out around the edge of the diamond, saying, "Is it clear? Is it clear? Is it safe?" And they report signals back to the root, saying, "I see a contact to the northwest." But it looks clear to the northeast and the southeast and the north southwest. And then the root says, let's go south. And then everybody does it like that. And so that's an act of synchronization, but it's a program. It's programmed in rather than being permanently part of the architecture.
Gotcha.
And so there's that flow back and forth of you become part of something bigger than yourself. You become part of a diamond. You play your role. You say, "Hey, I'm part of the dew line. I'm transmitting contact warnings up to the root so it can not go west because that would be really bad right now." That kind of thing.
Mm.
And then the signal comes back. Go east or whatever. So they do it anyway.
That's really neat.
Yeah, and for me in the trenches, developing this stuff day and week and month after month, there's so many echoes of things that happen at larger scales. There's so many echoes of stuff that people do, but and to some degree, I feel like it's sad that I can't express those all to people. I mean, because they're sort of like, nifty little simple examples of why cooperation is important, or why not being a dick is a good thing, because that helps you make a local coordination, helps you make a local synchronization, which allows you to be part of something a little bigger than yourself and have a little bit more success, like that. So it feels like a lot of the stuff that people used to worry about a lot, like free will and consciousness and the meaning of it all, like that, sort of pales in comparison to the basics of physicality. Like one of the first things that happened when I started doing the diamonds with the signals going up to the center is that when the diamond would undergo a growth spurt by changing the maximum distance from the root that's allowed from 6 to 7, and then all of a sudden there's a whole new growth around the edge. All kinds of things go weird when there's new growth out there because it wasn't really designed for that. It was designed for the grid being kind of steady. And sometimes the signals that are measuring is there stuff out there go off mistakenly, and they send signals up to the root, and the root decides, I can't go south, when in fact there's nothing wrong there. It's just like that. And I looked at these things and I see these things and it's like, wow, that's an itch. The thing has got an itch, like that, and it's itchy because it's having a growth spurt. It's tight in its skin, like that.
Wait, help me out here. So itch. Maybe you think about itches more abstractly than I do.
It's a phantom feeling. It feels like a contact. It feels like a bug. It feels like a mosquito or something on your skin. But you go there and there's nothing there.
I see.
Like that. And that's what's happening. These signals are going up to the center, which are even causing you to look, causing you to go away, causing you to react. But it's not real, like that. And that's happens all over the place. And, I didn't program it in. It just happens because, when you program these things, for robustness, you want to design it all so that as much as you can, it's self-stabilizing, so that no matter what state the thing happens to start in, it will have some direction to go to say, well, I'm not sure what's going on, but, there should be a guy to my north, south, east, and west, and there's nobody to my west. So I'm going to go ahead and put the guy to my west. I'm going to go ahead and fix it up. I'm not going to wait for a order to do this. This is just my view of things. And they do it. And if everybody does that, then the diamond grid heals itself. If it can, you can carve out a big hunk of it, and as long as you leave empty space behind, it'll just grow right back into it, like that. And I don't know, I forgot what my point was.
Well, so does it make you feel like you understand the actual world a little bit better? And is this a story that might resonate with other people?
Well, I want to believe that it is. I want to believe that this is the living computation story that, and the Movable Feast machine and the stuff that build with it, the demos, are examples to provide a second implementation. So I can talk to you about what it's like to have an itch, and you and I can agree, oh yeah, it's itches. But who knows what that actually accounts for. But if we can point at another thing, a separate implementation, and say, it's like that, then that actually has some bite. That actually narrows it down to make it more than just words. So that's the fantasy, is that there'd be a way to express this viewpoint that, this seems like a very basic, widely all-encompassing theory of everything way to look at stuff, that at least in potential can have this second implementation to make it more than just talk. We shall see.
Now, weird, I feel like past time, but there was a couple
We're
other things that I was
time.
wanting to talk with you about. Would it make sense to carve it up into multiple episodes?
Sure. I mean, if you want to go again, well, my feeling is, we've had some great guests recently, and we should still keep trying to get some great guests. But we also owe our audience like 2 extra episodes somehow. So maybe we should continue the conversation either, immediately next time around, or if there's guests, then another time out, something like that.
Okay.
If that makes sense. I mean, and again, busy, but like good busy. Yeah. Yeah, I was trying to figure out a title for this episode. It's like, let's blame AI. I think that should be the title.
AI is sucking up all our valuable time that we would otherwise be spending on AI.
That's right. Or AL.
There you go. AL.
All right. Well, hey, Michael. Well, it's good to see you anyway, and good to hear a little bit what's up. We'll get this out for the end of the month for the June episode, and then we'll try to keep it going.
Yeah. Maybe I should put like a recurring calendar event. Don't forget that.
We need a guest.
Yeah.
Like that, or we'll continue the conversation as well.
All right.
All right. Well. Keep writing your STEM thing. So can I sign up for your STEM thing, or does that
absolutely
have to be
no? There's just like a box you click on at the NSF site for like, what mailing list do you want? Like, we'll talk to anybody.
All right, so you can get me an URL, and I could put that URL into the title and metadata for this episode, so that other people could click on it if they wanted.
Sure.
Well, I mean, what the hell?
Yeah. No, it sounds good.
Okay, man. We will talk again. This was Computing Up. Thanks for listening.